Hello everyone, welcome to my channel, The Big Boolean Theory. This video is part of a lecture series on operating systems, and in this video we are going to solve another gate question. So this gate question was asked in the year 2004 for 2 marks, and it is related to CPU scheduling. So let's read this question. So the question goes something like this: consider the following set of processes with the arrival times and the CPU burst times given in milliseconds. So this is the table. As you can see here in this table, we have information about a bunch of processes. There are 4 processes: P1, P2, P3 and P4. We have the arrival time as well as the burst time. All of these are in milliseconds. So based on this given data, the question is that what is the average turnaround time for these processes with the preemptive shortest remaining processing time first, or SRPT algorithm. So first of all, shortest remaining processing time first is the same as shortest remaining time first. This word, processing word, is redundant. We are basically again talking about the shortest remaining time first algorithm, where the scheduler prioritizes the job which has the minimum or the shortest remaining time, burst time, right? And obviously, we know that this is preemptive in nature. So the question is asking what is the average turnaround time. So as we know, the turnaround time for a given process is the uh, time from which at which it enters the system to the time at which it completes. So turnaround time is completion time minus the arrival time. So this is the metric, and we are being asked the average turnaround time for all the processes. So we already discussed the shortest remaining time first in another video, right? So in this video we are going to solve this question. So the data that we have, I have written down the information that we have. This is the information about the 4 processes: the arrival time and the burst time. And the key points are that we are going to use the shortest remaining time first scheduling algorithm. And the thing that has been asked is the average turnaround time, right? So let us prepare the Gantt chart for this question. So first of all, we'll start with the process P1. It has arrival time of 0, right? At t is equals to 0, process P1 arrives, and as you can see, it has a burst time of 5 milliseconds. So we have not yet scheduled the process. So at t is equals to 0, you can see there is only one process in the system. All the other processes arrive at a later point. P2 arrives at 1, P3 at 2, and P4 at 4. So at t is equals to 0, when the scheduler is making a decision, it only has one choice. There is only one process in the system. So that is the process that will get selected, right? So, and till when process P1 will be allowed to run? Process P1 is allowed to run for 1 millisecond. Although it has a burst time of 5, will not let it run for the entire 5 milliseconds, because at t is equals to 1, a new process, that is process P2, arrives in the system. As you can see, at t is equals to 1, process P2, which has a burst time of 3 millisecond, has arrived in the system. So from t is equals to 0 to t is equals to 1, there is only one process in the system. So there is no further decision has to be made after decision has been made at t is equals to 0. But at t is equals to 1, when a new process arrives, now there are two processes, P1 and P2. And now the scheduler has to consider which process has the shortest remaining time, right? So for P1, we can see that it has executed for 1 millisecond. So the remaining time is 4 milliseconds. Whereas for P2, the burst time or the remaining execution time is 3. So the shorter one is P2. So P2 will be allowed to execute. And till when will the P2 process P2 be allowed to execute? Until the next process arrives. So the next process, that is P3, it arrives at t is equals to 2 milliseconds. So from 1 t is equals to 1 to t is equals to 2, we can be sure that P2 is the shortest process. So from 1 to 2, P2 will get to execute. At t is equals to 2 milliseconds, a new process arrives in the system, which is P3, and which has a burst time of 2. Again, the scheduler has to reevaluate the system. It has to consider all of the processes and allow or schedule the process which has the shortest remaining time to execute next. So let us look at these three processes, P1, P2, and P3. So which process has the shortest remaining time? As you can see, P2 also has executed for 1 millisecond. So its remaining burst time will reduce from 3 to 2. Now between 4, 2 and 3, we have to pick the shortest. So as you can see, obviously P2, which has a burst time of 2, is the shortest remaining, has the shortest remaining time, right? 2 milliseconds. P1 has 4 and P3 has 3, which is greater than that. So we will allow process P2 to run till when? Until a new process does not arrive in the system. So the next process does not arrive until 4 t is equals to 4 milliseconds. So from t is equals to 2 to t is equals to 4, we are sure that process P2 is the process which has the shortest remaining time first. So P2 gets to execute for 2 more milliseconds, that is from 2 to 4. And then it also finishes because its total burst time was 3 milliseconds. So from 1 to 4, P2 completes its execution and it exits the system. Finally, at t is equals to 4, process P4 has arrived in the system, which has a burst time of 1. Now, all of the processes have arrived, right? So, as we have discussed previously also, once all of the processes have arrived, we have global knowledge. That is, we have knowledge about all of the processes and their remaining burst times. So, shortest remaining time first algorithm now is no more a preemptive algorithm. We don't need to do preemption because the series of choices that we'll make will be optimal. So shortest remaining time first actually reduces to a non-preemptive shortest job first algorithm once all of the processes have arrived, because preemption is only required, that is preemption is only done when there is a chance that there is a better candidate in the system, and that happens only when new processes arrive. When a new process arrives, at that point there is a chance to reevaluate the process and see which is the one with the shortest remaining time. But once all of the processes have arrived in the system, then it is fixed. We know when we are scheduling that the one that we are scheduling is indeed the shortest remaining time, has the shortest remaining time, and that is not going to change. That information is not going to change because no new process is going to arrive further. So now what we have to do, we just have to schedule the processes in the increasing order of their remaining burst times. So P2 is already done. So considering P1, P3 and P4, we can now schedule them according to the increasing order of their remaining burst time. So P4 will be scheduled, which has the least burst time at this point, that is 1. Then goes P3, which has a burst time remaining of 3. And finally goes P1, which has a 4 remaining burst time. Right? So this is how the Gantt chart looks like. And now we have the completion time for all of the processes. So once we have the completion time, we also have the arrival time. We can compute the turnaround time using this simple formula, that is completion time minus arrival time. That is the total time that any given process spends in the system. And once all of these are calculated, we can compute the average. So the average turnaround time is 5.5 milliseconds. And in the options, we have the right option is option A. So answer is 5.5 milliseconds, option A. Right? So guys, this was it for this video. Thank you very much for watching. I'll see you in the next video. Thank you.